Thanks for coming. So today we have Xavier who will talk about something. Tree decomposition? Different tree decomposition, right?
Yes.
Yeah.
Thank you for the invitation. It's a pleasure to be here. And I thought I would take this occasion to talk about something that is not so recent. As you can see, the work is already 2 years old, but there was some recent development, so that's an occasion to revisit it. And so it's joint work with Mathilde Bouvel, Valentin Féray, and Florent Koechlin, 3 colleagues in France. Is there any issue with the live streaming?
저쪽 화면은 나오고 이쪽은 안 나오는데. 아, 예, now it works. So
this is joint work with Mathilde Bouvel, Valentin Féray, and Florent Koechlin, who are in France at CNRS. Mathilde and Valentin are like me at Nancy, and Florent is in Paris. And so this is a canonical tree decomposition for chirotopes. It's an application. So the combinatorial object here are chirotopes. So let me first introduce them. The idea is we want to use combinatorial methods to do geometry. So we're going to encode geometry into a combinatorial object. That's what chirotopes are. So you start with a planar point set, P. Those points have labels. The labels are pairwise distinct, so the labels identify the point. And the idea of a chirotope is that for every ordered triple of points, we're going to record a sign. The sign is computed, it's a sign of the determinant, and that will give us some rough information on the point. It will tell us whether the triangle, so chi p of PQR, will tell us whether the triangle formed by the point PQ and R is clockwise, oriented clockwise, counterclockwise, or is flat. And you can forget about flat, they won't happen in this talk. So we're just going to look at points in general position, no 3 aligned, and we just want to record that information. And what we call a realizable chirotope for a label set X is a map that assigns to every triple of label, ordered triple of label, plus 1 or minus 1. And we call this a realizable chirotope if there exists a point set for which this is the orientation map. Okay? So F is purely combinatorial, but there is this existential condition that makes this a bit tricky and give it its interest for us. Why we look at that is because that's a convenient way for when we're doing geometry to reduce a large variety of configuration or point sets in the plane, of all sets of endpoints in the plane, to just a finite number of distinct cases. Okay, and we can use this to try, and of course, this reduction will preserve certain properties. For example, if you give me the chirotope map of a point set, I can tell you which pairs of points define edges, segments that intersect. That is encoded in this orientation. I can tell you what are the points that are extreme on the convex hull. and so on and so forth. And just to give a taste, these are the 14 different chirotopes, realizable chirotopes of size 4. I should have said that, but if there is any question at any time, feel free to stop and ask it. So far so good? The object is clear? So the kind of question, and why do we look at that? One idea is that once you have a list of all possible chirotopes of a certain size, you can just examine every single one of them in turn, and you can therefore establish, by looking at them, certain properties of all sets of that size. And so this is convenient if you, for example, want to test a conjecture that depends only on orientation. It's convenient if you want to try to test some implementation of an algorithm. Interestingly, so there is a database of this configuration up to size 10, and one of my co-authors, Florent, he downloaded it and he ran it through some algorithm in Sage, and he could identify some bugs. Right? So, because you're going to run, if you run your algorithm on every single of those entries, you're going to test all the execution traces that are possible. So that's a much more efficient way to test an algorithm than to just take points at random. I'm coming back to that. So that's good? Okay. So there are three natural questions that turn out to be pretty hard for those structures. The first one is enumeration and even counting. We have an enumeration up to size 11, and that's about it. Nobody knows even how many realizable chirotopes there are of size 12. So we don't know how to count them. We don't have a general formula, but we don't even have the exact count for reasonable size. Even the asymptotics is hard. So we have known for 40 years that the number of realizable chirotopes of size n, you can write it as n to the 4n times some function that is sandwiched between two exponentials. The current bound have this with C1 less than 1 and C2 more than 1. So we don't even know if the number dominates or is dominated by n to the 4n. Okay, so we have the first order term, but there is some exponential noise on the line. That's the first non-trivial bound, and I'm not aware of any more recent bound or of any improvement on that. And even sampling is hard. Even if you want to just pick a realizable chirotope at random, not even uniformly, but just at random of size 20, it's actually more tricky than meets the eye. Okay? There's something, what hides behind that is a theorem called the universality theorem of Neuf. It tells you, well, it says the following. When you have such a map, when you look at such a map F, it's supposed to encode sequences of endpoints. A sequence of endpoints is basically a sequence of 2n real numbers. So you can think of a sequence of endpoints as a single point in a space of dimension 2n. And now in that space of dimension 2n, you can look at all those points that correspond to this function. It's what's called the realization space of that function. It's basically putting all the configuration of points with the same chirotope into the same space and looking at each configuration as a point. And now in that space of dimension 2n, you have an ambient dimension, so you can actually ask, is a space of configuration of points with the same chirotope, is it connected? That's a way to ask, if I give you 2 point configuration and they have the same orientation, can I move continuously from one to the other while keeping, without ever making 3 points aligned? And what Neuf's theorem tells you is not at all. It can be arbitrarily messy. So for any semi-algebraic set, there exists a function whose space of realization has the same petty numbers. So not only can it be disconnected, but you can actually choose a number of connected components. And for each connected component, you can choose a number of one-dimensional holes, two-dimensional holes, and so on and so forth. And there will exist a point configuration whose realization space will have that topology. So it's it's complicated. And Peter Shaw turned this construction into a proof of NP hardness. If I give you a function and I ask you, is it a realizable chirotope? That's an NP hard problem. It's not NP complete. We don't know that it's NP complete because we don't know if it's in NP. And the reason we don't know if it's in NP is that it's actually something stronger. It's ETR complete. So it's complete for the class of problem of existential theory of the real. And we don't know if ETR is in NP. Actually, if ETR is a problem, ETR were in NP, those two classes would coincide. So we don't know if deciding if a function is a realizable chirotope, we don't know if it's in NP. And that question is actually equivalent to being able to sample all the type. If you can provide me with an algorithm that takes as input a number n, and in time polynomial in n spits out a function, and if you can guarantee, so this algorithm has access to a pseudo-random bit string, and if you can certify that for every possible output, there is at least one bit string that produces this output, you basically proved that it's certifiable, so it's in NP. So sampling with full support, we don't know how to do that in polynomial time, and it's likely it won't work. It's not possible. And one thing that is pretty natural is to just try to take points at random and read of their order type. So you just take your favorite distribution, you sample points, and you read the order type. Experimentally, you can observe that this produces order types that are very concentrated. Out of, for example, for size 10, there are 30 million order types. And if you sample a billion type, you basically see 1/3 of them. Okay, and the most popular will show up 500,000 times. So it's highly redundant. Okay, and we could prove with Emo Wenzel a few years ago that if you sample a polygonal domain, a smooth domain, a Gaussian distribution, as the number of points goes to infinity, you will land in a vanishingly small subset of the function. Okay, so it's hard to sample. Which means it's hard to explore. If I want to try out configuration and do some computation on point sets through that mean, I don't really have good ways of enumerating or sampling this. And so that's the starting point. That's what we try to do with those decomposition tree, is to find a way to construct interesting examples. Make sense? Okay. It's basically geometry without points on its half. Okay. And so the way we do that is that we're going to try to assemble large realizable chirotopes out of smaller ones. And again, keep in mind that it's actually very difficult to pinpoint what makes a function a realizable chirotope because it's ETR hard. It's NP hard. Okay. One motivating example we had was counting triangulations. So when you have a point set in the plane, a finite point set, what we call a triangulation is it's a maximal family of non-crossing segments with n points on those points. And so that's basically a way of decomposing the convexol of your point set into triangles. It's the same. It's very well understood if you put your points in convex position. That's just a Catalan structure. We know lots of things about it. Okay. It turns out that which set of edges cross depending on the chirotope, so you can actually push the definition of triangulation to the level of chirotopes. You don't really need to discuss about the coordinates of the point. It doesn't matter. The only thing that matters is the chirotope. And there are many questions that are open. So, okay, we understand points in convex position, and that's about all we understand. We don't know what is the maximum number of triangulations that can be obtained. We don't know the configuration that is extreme. We don't know what the minimum number of triangulations. We don't know what are the extreme, and so on and so forth. Okay, so there's a lot that we would want to know. As you can see, on the low end, the gap is between, so we know that it's exponential. On the low end, we know that every point set must have at least 2.63 to the n triangulation, and we know, for example, having 2.47 to the n. On the high end, we have an example with about 9 to the n, and we know that every configuration has at most 30 to the n.
What is kappa?
So that for kappa is a chirotope. So any configuration of endpoints, that's the same. Okay, and that describes a set of triangulation of those. Okay, that makes sense? So we'd like to be able to build example with more triangulations, and we don't know how to describe them.
So when you say cardinality of the set of triangulation,
I'm counting the triangulations.
yeah, but you might have infinitely many triangulations.
So it's no.
For a fixed kappa.
For a fixed number of points. So for a fixed configuration of points,
Oh, I see. The
I
point
fix
is
the
points
point
are
is
fixed.
fixed. Yes. And I'm asking, so here, for example, if the points are in convex position and there are 6 of them, this is the number you get.
I see.
So when points are in convex position, does the number is maximized or minimized or somewhere middle?
It's 4 to the n, roughly speaking.
Isn't it Catalan number?
Yeah.
I forgot the.
So with my resolution, with my eyesight, Catalan is 4 to the n. Okay. And so it's neither extreme nor neither on the low end or on the high end, even though one may think it's a natural extremal candidate to be extreme. Interestingly, so when you look at such a question, the reason, so one way to define triangulation is you're trying to cut out the domain into triangle, but the other more interesting definition that is equivalent is you're looking at a maximal family of non-crossing segments. This has an immediate corollary. If you look at this edge, for example, in the point set, there is no edge that crosses it. That means that it is in every triangulation. Okay? So that's obvious for the edges that are on the outside. The example that maximizes the number of triangulations, the example with the largest number of triangulations that we know, has a lot of those edges, which is some kind of counterintuitive, because that means you have less room to flip edges and create new triangulation. So I suspect that there is some kind of streetlight effect there. This is an example we know with most triangulation because this lies in a corner of the space of chirotopes that we know how to analyze. It's under the light. It's under the light, so we see what's there. There's no reason. I can't think of any reason that makes this a good candidate for having the maximum number of triangulation. It doesn't make any sense to me. But those are the best examples we can build. And so this is what we're trying to do. We're trying to basically build another streetlight so that we can maybe find something better inside. Okay? So the way we work is we introduce this operator. So we're going to start with so the blue point on the left and the red point on the right. And we're adding to the blue point on the left an element here, x star. And we're going to basically tie them up by saying that to the blue point of the left, on the left, every red point looks like x star. And to the red point on the right, every blue point looks like y star. Okay, and there's a way to define this at the level of orientation. It's basically using this here, this map. So kappa is the function I'm building out of assembling alpha and beta, using in alpha x star as a substitute for beta, and in beta y star as a substitute for the point of alpha. And so if you give me 3 points from the x side, I just apply alpha. If you give me 3 points from the y side, I apply beta. Otherwise, you're splitting 3, 2. So I go to the side where there are 2, and I use a substitute for the third point. Does that definition make sense?
Are you saying that when you do this, then this is also realizable?
Yeah. when you do this, so it is realizable if and only if both alpha and beta are realizable, and the point you assemble, you use as proxies are extreme.
So that means on the convex hull, or?
Yes, that means they are vertices of the convex hull. Extreme is that.
Like, how do you realize it? Do you like put like in a very thin thing, or?
So what you want is something like this. Yeah, I paid him. What you want is something like this. You want that when you take the blue point without the proxy, and you draw all the lines, you want the red point to be on the same cell of the arrangement of those lines. So no line spanned by two blue points split the red point, because that would give you two red points that behave differently for one of the orientation. And so basically you start by realizing both of them, and then you move them apart. Okay? So what you need to do that is you need the proxy. You need to realize the blue point and make sure that the proxy is touching a cell that is unbounded in the arrangement of those blue lines. That you can always do by using some projective transformation. That's the only geometry you need to use there. Okay? And this condition is very nice, because that means we can start from basic, very simple, concrete example of point sets of chirotopes that we know are realizable chirotopes, and then we have a simple operation to generate more. And we are sure, because of this criterion, that we are always remaining within the space of realizable chirotopes. Okay? And this operation is actually associative, so we can make trees. It doesn't matter, we don't need to record to keep track of in which order we do things. We just have a tree. Okay? And so we can look at something like this. So this is the configuration, 36 nodes, each decorated with a realizable chirotop of size 9. This adds up to 254 elements, and if you zoom there, what you will see is something like this. So here, in each node, you get black points that correspond to actual point of these 254. And the green here is a substitute for any of the black points in that subtree. All the black points in that subtree, seen from this point, they look like the green one. And same the blue for the other subtree and the red for that subtree. And now if you're asking, okay, how does this point, and that point, do they turn left or right? I go to this node, where I have a representative for each of them, and they are distinct representatives, and I look at the orientation of those representatives. Okay, so I can actually compute. So this is a representation of a point set that exists. So there actually, I could, in principle, write a list of 254 points with coordinates that would have exactly the same chirotope as what I have here, but I may need a huge this difference in coordinates to actually represent them because of this pushing around, right? So this is what we gain by working with this tree representation. That make sense?
So here,
Yes?
how 254 is obtained? 36 times 7.
So 6.
But
Did I get it wrong? No, because you get in the leaves.
I see.
Okay. And now it turns out that. So now the question is, okay, so we now have a description of realizable chirotopes that we know exist. Okay, so if you ask me, if you give me 3 labels, I can provide you with the orientation. What can we do with that?
What is this number labeled? 106, 709.
How do we get
database.
those things of size 9? We go. So there is something called the order type database. It's maintained by Hoslin A. Scholler, and so he has up to size 10. Up to size 11. He has realization of all the realizable chirotopes. And so this is we picked this the guy with number 106709 from that database that we put there. We just pick them and drag them. Any other question? So one thing we can use this for is count triangulation. Okay, so if you look into how can we count triangulation of point set, it's actually not a completely trivial problem, right? There's a very nice algorithm, it's beautiful, by Alvarez and Seidel, and it does something a little bit non-trivial because remember that every point set has at least 2.63 to the n triangulation. So we can count them faster than just enumerating them. So it's a very simple aggregative algorithm that actually can be implemented, but it's exponential. The fastest known algorithm, and I don't know of any implementation, is by Marx and Mitzlow, and it's n to the root n. So it's in principle faster. I'm not aware of any lower bound for that complexity. And so what we did was we started with an implementation of that we do on the level of chirotopes that can work for a set of size 10, 11. It doesn't matter that it's exponential. We can actually run it. And we use the fact that if you know the information on the triangulation of this set, on the triangulation of that set, you can count the triangulation of the joint, of the bow tie. How does it work? Let's start with the triangulation, and let me color the edges. Green if they're between two vertices of x, red if they're between two vertices of y, and blue if they go across. Now, from this triangulation, I can make a triangulation for x union the proxy. I just shrink this set to a single point, and those blue edges, they will just converge to this point. Okay, and they cannot cross simply because every red point looks the same from the green point. That will tell me that I can shrink like this. So behind every triangulation of the bow tie can be projected to a triangulation of the left part, and similarly the right part. Now, for every choice of a triangulation of the left part and the right part, there is a way to reconstruct one, and actually several such triangulations. The question is, which ones? Well, the information you need are the degrees of those proxy points, the points that represent the other one. So here, you get 4 points for x star, 3 points for y star. So what we can show is that there is a bijection between the triangulation of the combined point set and the triple formed by a triangulation of the first part, a triangulation of the second part, and a inclusion maximal set of edges connecting the neighbors of x star and the neighbors of y star. And because every green point looks the same from red and every red point looks the same from green, we don't even need to record which are those neighbors. We only need how many of them there are. Okay. And so that means that the number of triangulation of the combined chirotope, we just sum over all choices of one triangulation of the left part, one triangulation of the right part, the number of possible set of edges going across. Okay, and there are many. The question is how many? It's basically a problem of partitioning integers in a certain way. Okay, because what can you do? You're starting with this edge, and now you have to decide how many edges you put to that, and that will tell you how you decide. If you skip a vertex, that vertex cannot be connected, it's not maximal. And at some point you decide that you had enough for this vertex, and so you pivot to the next vertex, and you continue. So it's just a partitioning problem. Okay. And now, what we want to do to iterate, so this is for one bow tie, and we actually want to do that for a tree. So we need to iterate this again. So what we need first for one bow tie is the information will be how many triangulations do we have, and for each of those triangulations we want to know the degree of the proxy for both sides, right? So we actually, this is information that is recorded in this generating series. And so or actually this polynomial, yeah, it's finite. So what this polynomial is doing is you're giving me a chirotope, you're marking a point, and I'm looking at all the triangulation of the chirotope, and I'm taking x to the power the degree of that marked vertex in that triangulation. Okay? So for this point set, there are exactly 3 possible triangulations because lots of edges do not have any edge crossing them. Okay, so this is fixed. So you can only choose what happens between those 3 vertices. And there are 3 choices. And so you get x3 here because there are 3 vertices, 3 attached edges, x squared here, and x to the 4 here. You get your polynomial. And so we get this formula. Number of triangulation of the combined point set is this sum where you get the coefficient from this polynomial. So if we know the polynomials associated with the 2 parts, we can get the triangulation. Now we want to iterate this, which means we want not only this number of triangulation, but we want the polynomial associated with kappa for a certain point, which we will then use to attach it to something else. Okay? So we bootstrap. It's essentially the same idea, it's a bit more technical, and we have to pay a bit more attention. The idea now is that, say we're looking at this vertex, we are trying to remove an edge that is attaching to x, and we know that the next edge will attach from this star. We introduce a parameter counting the degree of x star, a parameter counting the degree of v star, and we need to know if there is an edge between x star and v star. And so if this tells you how you handle the node with exactly 2 edges attached, if you have a node with 3 edges attached, well, then you get 3 marked points, you get a variable for each of them, and you also counting the degree, and you also get a variable indicating for each pair whether they form an edge in the triangulation. Put that all that together, and that works. Okay. And so from this information in polynomial time, we can get the number of triangulation of the combined point set. Which means that for this example here, we get the number of triangulation exactly in a few seconds. Interestingly, so Alvarez and Seidel, they actually implemented the algorithm and they performed quite a bit of algorithm engineering. So their algorithm is more general. It can handle any point configuration, but there's no point configuration of size more than 35 that they can handle in less than 10 minutes. Here we have 200 points in a few seconds for certain examples. Yes?
Are they also enumerating all these triangulations?
Sorry?
This sounds like a crazy number to me.
Yeah, this one, yeah.
Yeah, I mean, so when you say they managed to compute this exactly in a few seconds, you mean the number or also all the?
No, it's a number.
Yeah, okay.
It's an aggregation, right? So we have numbers we start with a node. There we basically have count the triangulation exactly.
Yeah.
And then we do that for each node, and then we apply this thing to aggregate. So in principle, you could also use that to enumerate by every time you aggregate, there's a bijection underneath.
Yeah, but enumerating these many objects is
Yes, we run out of sun before we're done.
Okay.
If we try to enumerate this with the best computer on Earth, we don't finish before the sun blows up.
Yeah, that's exactly what I'm thinking.
Yes.
So, but you managed to compute the number,
Yeah.
and even for computing the number, you're essentially kind of running this algorithm that's.
We run the algorithm on every node individually. So there we get 36 times 9, and that goes very fast. And then we do this computation to reduce each edge. And the time is polynomial in the description of your tree. So what matters is the number of edges you have in the tree, and it's polynomial in that, because those are the computations.
But did you verify that this number is correct?
Exactly. Prove me wrong. I dare you to prove me wrong.
Find the one more.
Yeah. No, you have to trust the proof, and you have to trust the implementation of the
They
code
haven't found
if you want to trust the result. So what we did
One more.
is we actually, for very small examples, we produce them as trees, but also as point set.
Mm.
And we run the Alvarez Seidel on the point set, and we run an algorithm, and every test we made like this, they matched.
So when you say trust the implementation, you mean this was verified in Lean? or
No.
something? Okay.
No, we trust.
Just check.
We look at the program and say, yeah, looks good. Okay, but yeah, if something crucial depends on this result being correct, that would be the way to go. Okay. Let me give you a second example. My three friends, they're from analytic combinatorics, right? So they couldn't resist doing this. So let's build a chain. Okay, and so the basic, so in every node I put the same chirotope. So it's basically a triangle with a point inside. And I attach them using two extreme points, of course. And sometimes I put the third point above, and sometimes I put it below. I didn't say it, but we have a theorem saying if you have such a tree, and every node is indecomposable or convex, and no convex nodes are neighbors, then the tree is canonical. So these trees, they satisfy this property. So every choice of up-down gives you a different chirotope. No two are equal. Okay? And for those, we can actually compute the asymptotic precisely of the number of triangulations, and they are all equal. Not only is the asymptotic equal, we can prove that the number of triangulations are all equal for every sequence of k. So you get 2 to the k choices of up-down. Those 2 to the k number of triangulations are equal. I don't know how to make a bijection. Okay. And we can actually, as n goes to, as the chain grows, we can give you the precise asymptotic. This is an example of what's called the kernel method in analytic combinatorics. So basically, you start with you write, so Pn of u is just a generating polynomial of this chain when you have n nodes, and where what you're marking, u is counting the degree of this guy. Okay? And you get this recursion coming from this definition. And what you can do is you introduce another variable. I think they call this a catalytic variable. And that turns each of your Pn into a function, f of ux, which is this. X is not counting much, it's just related to this n. And so you now, what was previously this and that, is now gathered into a single term with some rational function in front. And what the kernel method is doing is you find certain value, certain function u of x, parameterize u of x, that will cancel this and therefore get rid of that. And that will give you certain recurrences between f1 of that u of x and this term. And from that, you can get the asymptotic. Okay. And fun fact, it doesn't depend on this choice of up-down. Okay? Okay, so let me pre-wrap up. Okay, yeah. So what we have is, so these chirotope trees, they're a way to build large chirotope from small one. So what I mentioned quickly, but I didn't dwell on, is we can prove that it's well defined in the sense that not only is it associative, so that you can actually, you don't need to record the order in which you make the operation, but if you apply operation which is whenever you have a node that's decomposable and non-convex, you split it. And whenever you have two nodes that are convex and neighbors, you merge them. If you apply this, you get stuck at some point, and no matter in which order you do that, you will get stuck at the same tree. This is confluent. This is a set of rewriting rules that's confluent, locally confluent and therefore confluent. And so this means that we even, if you give me two trees and they satisfy this, are canonical in the sense that they satisfy those two rules, decomposable, indecomposable, or convex with no neighbor convex, I can actually tell you whether they are the same chirotope or not.
So what is indecomposable?
It means that you have a chirotope that cannot be written as a bow tie of two other chirotopes. This you can test geometrically by asking, is there a split of your points that has the property that no line from no line through 2 points of one side separates 2 points
You're
of
not
the other
allowed
side.
to do 1 point in one side.
And you're not allowed 1 point in one side.
Okay.
Yes.
Or else I think I could build anything, no?
Yes.
Yes, okay.
Yes. Okay. So this can be used to compute triangulation in practice or even analyze them with combinatorics. We could estimate the number of chirotopes that are decomposable, and so it's basically a fraction. It's close to. We believe this is the right order of magnitude. So it's a fraction 1/n3 of all chirotopes. This actually seems like a lot, because we only know the number up to exponential noise. So getting all of them up to polynomial noise is a lot. You have to bear in mind that most of them have a trivial split into a node of size 2 and another node. So if you really want to decompose chirotopes that decompose into very small pieces, I expect there are many fewer of those. When you look at those that decompose a lot, most of the complexity goes in the tree. And so it's easy to realize that there are, if you were to realize them, they would be almost in convex position. Because if you take 4 vertices, 4 points, for those 4 points to not be in convex position, that means that you should have a node containing 1 point, and the other point should be in the 3 subtrees. Okay? And now if you have a tree where every node is of degree 1, 2, or 3, no more, and you take 4 nodes at random, uniformly at random, it's very unlikely you get this. Okay, so that's something we can infer from those guys. Of course, if you're willing to increase the degree, then you're increasing the odds that it's not in convex position. Okay. And so, some recent follow-up. Emery Johan and Yann Marin saw this paper, and very quickly they realized that you could get essentially this result from very standard machinery developed for symmetric crossing families. So we had to prove a lemma to prove that the process is confluent, and that very lemma is what's proving that we are dealing with what is called crossing symmetric family in certain settings. So this falls within a very well-studied setup. There's also an alternative decomposition method that we were working on still with Mathilde, Valentin, and Florent. And we discovered recently that Hong-Duc Bui had been exploring the same idea. So let me tell you a little bit about that. The example that achieves the largest number of triangulation is what's called core chain. So Daniel Rochman and Manuel Wettstein, they designed those two operations. So when you take these blue and red and blue sets, they combine them, they define 2 ways of combining them, which are like this. So what you should see here is that every line through 2 blue passes below the black point. On every line, below the red points. On every line through 2 red passes below all the blue points. And these things are called chain because all the edges here, blue and red, are fourth in any triangulation of that point set. And when you're counting triangulations, that means that you can count separately the way of triangulating this, this, and this. This is a straight line. That's what allows them to do the counting efficiently. And so that you can extend, and that's what we had been doing separately, and we're currently trying to merge all of this. And you can do the same by, instead of taking chains, you can start with arbitrary chirotopes, and you can merge them in a way that they're actually splittable. Okay. And what we gain by doing this is that we could, for example, take the example with the construction that is a double circle, which is conjectured to minimize the number of triangulations. And so it's basically you take n points in convex position, so k points in convex position, and you look at the middle of every edge, and you put a point slightly inside for each edge. So you get 2 k points. This has about 12 to the k triangulation, but record that this is for 2 k points. So this is the square root of 12, so the basis of the exponent. And we could get, for example, using these operations, the exact asymptotic of the number of triangulations. Okay. All good? So let me finish with just a few open questions. So I think, to me, those chirotopes, they're really an interesting combinatorial object coming from geometry, and it's interesting to geometers. I'm from the geometry side. So I don't know if I can get you interested, but it turns out that so we have the starting point of this work was, what about modular decomposition of graph? Could we apply them to this? And a few years ago, with other colleagues, we did the same thing with limits of graph, limits of dense graph and graphons. It's also a framework set up, defined for graph, that we could apply to chirotopes. So they still support, they're a bit similar to graph in some sense, and they're very different because of this existential aspect. Okay? And so here are a few questions. The global meta question would be, what's your favorite method for studying discrete objects, and can it be adapted here to say something interesting? So, example of things we don't know, how to count them accurately. Are they in NP? Is there an analog to the Marcus-Tardos theorem? This comes from permutation patterns. You fix a pattern and you forbid it in permutation. There was a conjecture by Stanley and Wilf that this should kill most of them, and that was proven by Marcus and Tardos. We could do the same here. You fix a chirotope, a small chirotope, and you're looking at how many chirotopes do not contain it. In the sense that deleting points would give you something isomorphic to them. It's open. We expect that if you fix any planar probability distribution and you sample point IID from that, that will always concentrate. We could prove it for a number of distributions, but we used heavily results from stochastic geometry. People in stochastic geometry proved very good estimate on the number of extreme points with concentration bound. We could leverage this. We could actually determine exactly the average number of extreme points in a chirotope. If you pick a chirotope of size n uniformly at random, we know it has exactly 4 minus some small constant that we can compute extreme point on average. And so we could compare this statistic to random polygons. Of course, what are the maximizers, minimizers for number of triangulations? How could we build a street light that is away from convex position? And if you remember the very first definition of the bow tie operator, it says, well, if you have 3 points, there must be 2 on one side and 1 on the other side, so you can use the proxy. In 3D, there is a similar thing. There are similar orientation function, but it's a function on 4 points, which means if you want to do the same thing, you have to deal with 2 plus 2 split. And we couldn't figure out a way to do that, because the order matters. So, and that's it. Thank you for your attention.
Thank you. Any questions?
So So we have table base for almost 11 points, and so we observe that table base and see we have several parameters. So for each configuration, we have number of triangulation and also maybe number of extreme points, and then we have nice decomposition. We can decompose the bow tie and this kind of thing, and then we look the table base and choose some extremal example and make some like example with large number of triangulation or small number of triangulation. Then this method does not work for building existing bound.
So let me mention what we tried. So what Manuel and Daniel did here was the reason they call this coarse chain is you start with segments, then you pair them up and you do a joint thing. So on all pairs, and then you do a wedge thing on the next level, then you join, then you wedge, and so you get something that looks like a bit like a coarse chain, but very discrete. And this they could analyze, they get this 9 to the or A to the n. Now, if you just look at the small example, say of size 8, it is not so it shows up in the list and it's not extreme. There are other examples of size 8 that have more triangulation. So they couldn't do anything with it, but with our generalization, we could actually take their tree and cut out the bottom part of size 8 and replace it by triangulations that have more, with chirotopes that have more triangulation than what they use. And very quickly, we get below what they get. And we can't, so we try to analyze configurations that are in the vicinity of what they had, and we couldn't beat them. So we played with this kind of thing. We couldn't make any general analysis. Let me also mention that this kind of analysis here, we don't know how to perform it if they are not of degree 2, of degree 3, if there is branching. So we don't have a general formula like this that we can analyze asymptotically.
Did you try to look at something like direct linear crossing number or something like this?
No. The other problem we tried to work on at the level of trees are halving lines. And we couldn't figure out the number of halving lines in a bow tie from the number of halving lines or from parameters of the two paths. So if you've never seen this, it's a fascinating open problem in discrete geometry. You have a set of endpoints in the plane, and you're looking at the way of splitting it into two parts of equal size. The question is, what is the maximum number of ways you could split it? What is the point configuration that maximizes the number of ways in which you have a balanced cut?
I mean, you just rotate and
There are examples with a superlinear number. Yeah. So lower bound is n times 2 to the root of log n, and upper bound is n to the 4th. And I don't think it moved it doesn't move in the last 30 years, I think. And so that problem we couldn't encode.
So for this, can I ask something? Yeah, so for this butterfly operation, I mean, you have this condition that you have to choose one extreme point on both sides, right?
Yes.
But what if we just draw points set on the sphere, right? Then we don't have to have an extreme point, or like on the sphere everything can be seen as extreme. And
Yes. So I don't know how you could extend that to. So there are abstract models of course of points on the sphere. We haven't tried to extend it.
I see.
So the trick is to have a way to. So what you're really after is a statement like this, right?
Yeah.
Like
what I imagine is like when you rotate the sphere, this type doesn't change, and then stereographic projection will.
But
So
then
if
you're
you put
changing
the-
the order,
Oh, is it?
If you put of course all your points in the same hemisphere, then you're back to this.
Yeah.
So right? So you,
All the time.
but so if you actually have a point set that surrounds the origin, then I don't know how to do it.
Yeah. I have another question. So typically when we have 3D composition on graphs, we use it for many algorithms like optimization problems or whatever. So I wonder whether like this could be like given a 3D composition, maybe you can use that to solve some algorithmic problems. Or
Yeah. So we don't have any example, but I wondered about that too. For example, could you have something that goes fast if you say you have when most of the complexity goes in the tree. So in every node you have a constant number of points, k,
yeah.
and yes.
Like for instance, like Erdős-Szekers theorem, like if I wanna find the largest set forming in convex set,
Largest set in convex position.
Yeah.
That's
like given many points, I wanna find maximum set in.
maximum subset in convex position.
Yeah.
Okay, so that's hard. I'm not familiar with the complexity of this.
But even on trees, or
When you give 3D composition, then
small.
Yeah.
It is a click decomposition, right? So these 3 decompositions, if you think of them as the ternary relation which tells you is it clockwise or anti-clockwise, I think it is a click decomposition. So you should be able to.
yeah. So the information is all there, right? So I don't know whether the efficient algorithm will be able to find the largest subset, right?
So about triangulation, if we give some additional constraint like the triangulation should be regular, then is there any no upper bound or lower bound?
Not that I know of. I know there was a recent, so a few years ago, people looked at partial triangulation. So you want a point set, and now you're taking a triangulation, but you're allowed to skip certain interior points. So, and the configuration that maximizes this, I think, was it points in convex position? So there was some. I think Andrzej Kupawski was one of the also that proved that. So there was some variant where recent results were established.
Any other questions?
So it doesn't seem like you're actually using anything about realizability here, right?
I know.
It
Actually,
should all be done for oriented matrix. I don't see any.
yes. So that we do.
Uh-huh.
There's one thing we cannot do. Let me mention that. This is what we cannot do. Because here, to get this inequality, we use a lower bound on the number of extension of
So that's what
realizable
you were trying
character.
to do.
And that's what we were trying to do. And that's why I was interested in trying to do it. So that's an interesting side of the question. When you take a realizable chirotope, it always has at least n to the 4 extension. Because you pick a realization, you draw every line through 2 points, and that will divide the plane into n to the 4 region. I'm ignoring constants. And when you place the next point in different region, you will get different chirotopes. And actually n to the 4 is about the right number because the total number of chirotope is n to the 4n. So when you iterate n to the 4, it matches. Now if you go to oriented matrices, also have chirotopes, they are more general. And there we can also prove that every one of them has at least n to the 4 extension because they can be realized in a topological affine plane. But we don't have a better lower bound, and the natural lower bound should be exponential because the number is 2 to the n squared, roughly. So we should, what you expect, the typical real oriented metric of rank 3 should have an exponential number of extension. They should. I don't see why all of them wouldn't have one, and we can't prove anything better than n to the 4. And that's what we need to have a similar estimate on the decomposables.
Alright. Any other questions? If not, let's thank the speakers.